video, we are going to be taking a look at an example. We're going to be applying the vocab that we have just gone over. So the first thing I would like us to do is answer the question, how does the population N change with time? So we are looking at the graph that is on the right-hand side of your screen. This graph shows the population N equal to N of D in thousands of animals of a particular species on a protected reserve as a function of the date D. So when I look at this first question, how does it change with time? Well, time is the date, so that is the x-axis, the horizontal axis down here at the bottom of the graph. And how does N? Well, N is the population, the number of animals, and so this axis is our N, or our population, which is also what we would remember as the y-axis. So I want a one-word answer. How does it change? Think back to all of our vocab: increasing, decreasing, constant, concave up, concave down, point of inflection, minimum, maximum. What one word? Well, the entire thing is increasing. And so that means that the number of animals increased over time, sometimes fast, sometimes slow, but always increasing. Next question is, when was the population 80,000? So on my n-axis, here's 80,000. I'm going to attempt to create a straight line and bring that down. And it looks like my lines aren't 100%, but right around 1985. So I would say 1985. And then it asks us to write this in function notation. So this is where I'm really referring to all the notation around the graph. So my function is N, number of animals based on the date. So N is my function. The date that I was looking at was 1985. It goes in the parentheses because that is the input. And then the answer of that is 80,000, because the y value is the output. And so this is really a review question from last week where we went over function notation. Next thing we're asked is, where is the graph concave up? So here we have to think to what our word means, and concave up would have a cup shape. And it's not a real distinct cup shape, but a little bit of that curvature creating a cup. And I would say that is from 1970 up to 1985. So 1970 through 1985, the curvature there creates a bit of a cup shape. And then we're asked to explain, how is the population changing? So in this section, it is increasing because it is going uphill. And to get that curvature, most of the time it looks like it's increasing at a constant rate, and then right around 1985, it increases. And that's what gives us that curvature. So increasing at an increasing rate. So the increasing rate is describing that the slope gets steeper. So then next question, where is the graph concave down? Well, concave down is if I would imitate it with my hand to get my fingers to bend that way, I would have to have my palm down. And so that looks like it would go from 1985 through the end of the graph, which would have been 2010. And so how is the population changing here? Well, it is increasing because the entirety of the graph is uphill. But we see here that in the 80s and 90s, it is increasing pretty quickly, and then it starts to level off in the 2000s. So it is increasing, the slope gets flatter, so at a decreasing rate. So we described where it was concave up, where it was concave down. that means there's a point of inflection, because the point of inflection is where the concavity changes. So the point of inflection, I'm going to abbreviate that as POI, point of inflection, would be the ordered pair of 1985, 80,000. And so when I look at this ordered pair on the graph, that first one we identified right here, this guy is point of inflection. And looking at this question specifically, it says when. So when is asking me about the time. So I would answer that question if it happens in 1985. And then it asked me to explain this point in terms of the growth rate. So the growth rate is the slope. So that's why we had the slope was an increasing rate and then the slope was a decreasing rate. And that change from increasing slope to decreasing slope happens at the point of inflection. So the point of inflection, and this is a really key point, the point of inflection has our maximum slope or our maximum rate of change. That means that that point of inflection is happening at the very steepest point on our graph. So right in here, this is where our slope, our rate of change, is the steepest ever. And so that's something that's going to come up again in the course. So I'm pointing it out to you now. You want to associate that change in concavity with the point of inflection with the maximum rate of change. And then it asks us, what is the environmental carrying capacity? The language here is very specific to this problem. So we are told in the beginning of this problem is a particular species on a protected reserve. And so the reserve can only support a certain number of animals. And so we are looking how many animals can this reserve support. That would be the environmental carrying capacity. The environment where they're located is only large enough, that reserve, to support so many animals. And so what I have dotted into the graph here is what appears to be a glass ceiling. So it's not really drawn, that's why we call it glass, because it's there, but you don't physically see it. And it's a ceiling because it's something that graph comes up against and then it can't pass. So it acts like a lid on the function. And so the glass ceiling that we see here looks to be like 140,000 animals. So this environment or this reserve is large enough for 140,000 animals. And then the population is not going to have enough food and space to grow beyond that. Now, this environmental carrying capacity is a concept that shows up in many different contexts. And so this idea is called the limiting value. And it's different than a limit in calculus, although it's related, but it's called limiting value, and it is where we have that lid or that glass ceiling on a function. And so the function is not able to go past that. And again, that's a concept that we'll see numerous times throughout the course.